In this section, we'll discuss Kepler's laws. You've probably heard of these from physics class. These are the laws of planetary motion. The point is we will deduce these laws using Newton's law of gravitation. The first thing we need to do after we state the laws is review ellipses. We'll start with the definition of ellipse from geometry and then show how that gives the Cartesian definition of an ellipse you're used to, and then we'll go ahead and show what the definition of an ellipse is for polar coordinates. So let's start by stating the Kepler's laws. The first law states that a planet revolves around the sun in an elliptical orbit with the sun at one foci. We'll see later a picture of this to make it more clear. That'll happen with all of the laws as we go through. The second law states that the line joining the sun to a planet sweeps out equal areas in equal times. So let's quickly see a picture of what this is saying because it's a little bit complicated. So let's start with our ellipse. So this is the path that the planet would be traveling on. We'll put our sun at one foci, like this. And then suppose we have our planet that's traveling along the orbit here. So what this is saying is that in an equal amount of time, so if I move the planet from here to here, this amount of area that's being traced out during this time, if the planet's way over here on this other side, the equal amount of time has to give you equal areas. So it's going to be a little bit thinner over here because you're going further out. So that's all that this is saying, is that the amount it travels in equal time has to trace out equal areas. And finally, the third law states that the square of the period of revolution of a planet is proportional to the cube of the length of the major axis of its orbit. Don't worry so much about this one right now. We'll come back and this will make more sense when we actually put these into equations. So now that we've gone ahead and we've stated the laws, we'll restate these when we get ready to prove them. But for now, let's go ahead and introduce ellipses from the geometric point of view. The geometric definition of an ellipse is that it's the set of points in the plane, the sum of whose distance from two fixed points, the foci, is a constant. So our foci will be F1 and F2. And we'll go ahead and draw these in the plane here. So here's F1. And then we'll put in F2 as well. And so points on the ellipse are anything that are some fixed distance away from these 2 points. So you take the distance between a point on the ellipse. So here we'll draw up to some point on the ellipse. So the length of these distances here, this distance plus this distance should be a constant. So if I draw all the points that are the same sum of distances like that, those will be the points on the ellipse. So for instance, let's get rid of these lines that we started with and redraw to see what's going on with the distance here. So if I take a point over here on the ellipse, the sum of this distance plus the sum of this distance here should be the same as the sum of this distance plus this distance. So that's how we know these are the points on the ellipse. Okay, and so that's true for all of the ones going across there. We can go ahead and represent this in terms of equations as well. So let's take a point P up here and a point Q down on the other side here. And so now the distance between P and F1 here plus the distance between P and F2, this distance, has to be the same as the distance from Q to F1 plus the distance from Q to F2. And this has to be a constant number, so we'll just put this to be some constant for now. Now that we have the definition of an ellipse from a geometric point of view, let's go ahead and get that and see that this is the same definition as what you're used to from the Cartesian xy plane. So let's let F1 and F2 be the points that are the foci, and we'll set these to be plus or minus c, 0 in the xy plane. We'll let the distance that any point on the ellipse is from these two foci, we're going to have that to be 2a, and we'll let px be just x comma y be some point on the ellipse. And so we need an equation that describes p in terms of Cartesian coordinates. So here's our definition of the ellipse, that Pf1 plus Pf2 has to be some constant. We're going to call that constant 2a. The reason the 2 comes in there is it just makes the equations work out nicer to have the 2 there. There's nothing important about that. So now we'll just start working on putting this actually into Cartesian coordinates. So we're going to translate this equation up here. We're going to translate that first into what does that say in terms of the xy coordinates with p. So the distance pf1 is given by x minus c squared plus y squared, and take the square root of that for the distance. And then you have pf2, which is x plus c squared plus y squared, the square root of that. And then that whole thing should be 2a. So that's just using the definition that we already have and just putting it in terms of x and y. And so now what we're going to do is we're going to go ahead and simplify this through a bunch of algebra. So the first thing we'll do is move this equation, or this part, over to the other side of the equation. So now we're just going to continue to simplify this equation. So we have the distance from P to F1 that we saw before. And we go ahead and bring the other part of the equation over to the other side, as we said. So this is pretty simple so far. This is really just messing around with the algebra to make it look like something you recognize as an ellipse. There's nothing complicated here. So the next step is to square both sides of this. So when we square the left-hand side, we'll just get rid of the square root. And when we square the right-hand side, we'll have to FOIL it out. So we'll get a 4a squared from squaring this part. And then when we FOIL, we'll get this one times this one times this one, and this one, and then the same thing again. And then finally, we'll square this last one and get rid of the square root. So that's all that we just get from FOILing out. And then we just continue with the algebra to simplify things. So get everything that doesn't have a square root with it on one side and simplify. And that'll give you the following. So you get a squared plus cx is equal to a times the square root of x plus c squared plus y squared. So again, just simple algebra here. And now again, we want to get rid of the square root. So we've got the square root by itself, so we square both sides again. So we get a squared plus cx squared, and now I'll get an a squared, and then we'll get rid of, by taking the square, we'll get rid of the square root here. And now it's just a matter of simplifying this further. So go ahead and work this out and simplify and group all the x squared together and the y squared together, and we get the following. So this is getting much closer to looking like an ellipse from what you remember from calculus class. So here we draw out the ellipse. So remember that the one foci is over here at C, and we know the length from here to here is A. And so we just go ahead and define B to be this part over here. So we get the equation B squared is equal to A squared minus C squared. And so I can go ahead and plug that into the equation we found on the previous slide, or previously, and we get that b squared x squared plus a squared y squared is equal to ab quantity squared. So now just go ahead and divide through by a squared b squared, and we get x squared over a squared plus y squared over b squared is equal to 1, which is exactly the form for an ellipse that we knew from earlier in calculus class. It turns out it's much easier to do Kepler's laws if we work in polar coordinate form. So we need to put the ellipse in polar coordinate form. So first we're going to go ahead and give the definition of an ellipse from the polar coordinate point of view, and then we'll see that it's the same thing as what we had before. So let's let F1 be a fixed point. This will be one of our foci. And we'll let L be a fixed line. This is going to be called the directrix. And we'll define the ellipse in terms of these two terms. Okay, so we're going to make sure this is all in one plane, so you can think of it just as the xy plane for now. Okay, so we'll pick some number e, and for us, we're going to go ahead and take this number to be something that's less than 1, and that will give us an ellipse. And this is called the eccentricity of the ellipse. So the points on the ellipse are going to be given by the following equation. We want the distance from P to the foci divided by the distance from P to the line to be the exactly equal to E, our eccentricity. And we'll see some pictures on what this looks like as well. So this gives us an ellipse. Now we could also get a parabola or a hyperbola. So if E is equal to 1, we get a parabola. If E is bigger than 1, we get a hyperbola. But we're only interested in ellipses, so we'll always take our E to be less than 1. So here we'll start with our xy axis. We'll put the foci F at the origin, and now we're drawing our directrix over here. So this is L, and this is given by the line x is equal to d. And so now let's take some point P that's actually on our ellipse. So this will be our point P right here. And now note the distance between the division of the distance between P and F and between P and L needs to be the eccentricity, so this will give us our ellipse if we trace this out. But we'll look at the geometry a little bit here. So if we let this be, this distance here will of course be r, and then this angle here will be theta. And so we can write out the distances here. So I know that the distance down here from here to here is r cosine theta. The distance from here to here is d. So that means this distance that I'm going along here, this has to be d minus r cosine theta. Okay. Now if we use the picture from the previous page, we'll have that P over F divided by the distance P over L. We replace that with what we found from the picture, so r over d minus r cosine theta, and this is equal to E. We now go ahead and simplify this sum, so this equation is equivalent to, go ahead and solve this thing for r, and you get ed over 1 plus e cosine theta. So this is our form for an ellipse in polar coordinates. So we'll come back to this. You'll see this in Kepler's laws. This is how we'll show the planetary orbit as an ellipse. We'll get it in this form. But now let's go ahead and convert this to Cartesian coordinates so that you see this actually does give the same thing that we got before for an ellipse. So again, this is just a bunch of algebra. So let's just go ahead and square both sides. And we'll go ahead and square both sides of this, and we'll get the following equation. So take the top equation on this page, multiply through by d minus r cosine theta, and square it. And now substitute in. We know that r squared is x squared plus y squared. We know that r cosine theta is x, so make that substitution in. So now we have something that's in Cartesian coordinates, and now it's just a matter of simplifying this and playing around with the algebra to get what we want. So just continue to work on the equation we had before. Go ahead and square out the d minus x squared, FOIL that out, and we get the following. We get x squared plus y squared is e squared d squared minus 2dx plus x squared. And now we just continue to simplify this using algebra. Nothing complicated going on here. So just FOIL this out. And now we'll go ahead and see this equation is equivalent, so we'll bring stuff all onto one side. So we have the x and y terms all on one side, and then the constant term by itself. So we get 1 minus e squared x squared plus 2e squared dx plus e squared y squared, or plus y squared is equal to e squared d squared. And now we divide through by 1 minus e squared to get the following. And the point here is that we have the y squared by itself, but the x squared has an x term with it as well, which doesn't look like our form for an ellipse. So what we're going to need to do is complete the square, which is kind of a giant mess. But we'll go ahead and do this and skip most of the steps out of here. You guys can complete the square by hand, and that'll allow us to have this in a nice form. So once we go ahead and we complete the square on this, we'll get the following equation, which looks closer to what we're hoping for the ellipse. So we get x plus e squared d over 1 minus e squared, the whole quantity squared, plus y squared over 1 minus e squared. And you simplify this down on the right hand side and you'll get e squared d squared over 1 minus e squared squared. So when you first complete the square, it's not going to look this simple, but you can simplify it down to this. Okay? And so now let's rename some variables. So let's set h to be minus e squared d over 1 minus e squared. And we'll set a squared to be e squared d squared over 1 minus e squared quantity squared. And then we'll set b squared to be e squared over d squared, the whole thing divided by 1 minus e squared. And then when we do this and we simplify out, we'll get the following equation for an ellipse, which is x minus h quantity squared over a squared plus y squared over b squared equals 1. And this is exactly what the equation for an ellipse should look like if you're off center by a little bit. So you've moved the foci to be at the origin. That's where this part here, the x minus h, comes from, because you've shifted where the foci is to put it at the origin. But you haven't shifted it up or down, so you just have the normal y squared over b squared equation. So that completes the basics on the ellipses that we need to know and understand in order to actually work through Kepler's laws. So now we can actually start working towards using Newton's laws to prove Kepler's laws. So the first thing we'll do is we'll go ahead and recall Newton's laws now. So we don't need all of Newton's laws of motion to do this. We really are just mainly going to use the second law of motion here and the law of gravitation. So just recall Newton's second law is just force is equal to mass times acceleration. And the law of gravitation is just that the force due to gravity of an object is equal to minus the gravitational constant times the product of the two masses over r cubed. So r here is the length of the radius vector multiplied by r the radius vector. And of course we usually want to use unit vectors, so we'll go ahead and switch that out. So if I use the unit vector, that will cancel out one of the r's, and then I'll have a unit vector there. So r hat is r over the length of r. Okay. So those are the laws we're going to want to use here throughout this proof for Kepler's laws. Our first goal is to show that the orbit has to lie in a plane. So let's start off by combining the two laws, the second law and gravitation, to write the acceleration vector is minus g times the mass over r cubed times the radius vector. Okay. So this immediately tells us that the radius vector and the acceleration vector are parallel because they're just differing by the multiplication of this constant out front here, the minus g m over r cubed. Okay. Okay, so in particular, since they're parallel, we know that r cross a has to be equal to 0. So we have the following calculation. If I take the derivative with respect to time of r cross v, remember, even though I'm not putting in the t's here, these depend on t. So this is just the product rule. So this is the derivative of r cross v plus r cross the derivative of v. But we know the derivative of r is just the velocity, so this is v cross v, plus the derivative of r, we know the derivative of velocity is acceleration. And the whole thing is 0 because any vector here crossed by itself is always 0. And we just said above that a and r are parallel, so r cross a is 0. So we get the whole thing being 0. Okay, so and just remember, these are all functions of time even though we're not writing that in. Now since we have the derivative with respect to time of r cross v is equal to 0, this tells us that this doesn't change with respect to time, so this r cross v has to actually be a constant vector. Okay, so even though r and v change with time, the cross product does not change with time. So this is some constant vector. We'll go ahead and call that constant vector h. Okay, so h does not change with respect to time. Okay. So now what that tells me is that since h is the cross product of r and v, that tells me that h and r have to be perpendicular and v and h have to be perpendicular, which gives us what we want because we know that the motion of the planet is given by r and v, so those are both perpendicular to h. And so that tells us that the motion of the planet is actually in the plane that's perpendicular to h. Remember when we talked about planes in R3 before, we said that a direction vector, a normal vector to the plane, actually determines the plane. So in this case, this normal vector is actually h. Okay, so this completes our first goal of showing that the orbit is actually lying in a particular plane. It doesn't go up and down out of the plane. Now we're ready to go ahead and prove Kepler's first law. So this is a bunch more algebra and properties of vectors to get to. So before we prove the first law, let's just recall it quickly. So this is just saying a planet revolves around the sun in an elliptical orbit with the sun at one foci. So here's the path of our planet, and we'll go ahead and put the planet over here, and then we'll put the sun at one of the foci. And so there's the sun. And so this is just telling us that the planet moves along an elliptical orbit around the sun. Okay, so we just need to prove, we know it moves in a plane now, we just need to prove that this orbit is actually an ellipse. So let's go ahead and write r as the magnitude of r like we did before. This is going to be typical through the rest of this talk. If there's no vector on the top of it, it's the magnitude of the vector that went along with it. Now we're going to spend a lot of time simplifying some of the equations we had. It's not necessarily so motivated, but we'll see where we're going with this at the end. So let's recall that h, this constant vector, is r cross v. And we can go ahead and simplify this sum. So I can write the vector r as the length times the unit vector. And then I can write v as r times the unit vector r prime. And so go ahead and write out that this part over here, I can use the product rule on this because this is a function of t and this is a function of t as well, the r hat. And so use the product rule on that to get this here. And now go ahead and take the cross product and distribute this across the cross product. And note that the second part here, when I distribute the first here, the r hat, to this one over here, this is 0 because r hat cross r hat is equal to 0. So this simplifies this down some. So we're just in terms of r, and we just have unit vectors now. So now consider the vector a cross h, and we'll go ahead and use what we did on the just before to simplify the h part and replace it with the r squared r hat cross r hat prime. And then we can also simplify, we had the equation for A before using Newton's law of gravitation, so we'll replace that because that also has an r hat in it. So we get over the r squared and then we get r hat. And so go ahead and cross that through. And then we'll just go ahead like before and distribute this over here and then over here. And remember the r hat cross r hat here, that will be 0. So that goes away. And note that the r squared in the denominator here cancels with the r squared here. We can move the constants. So now what we'll do is we'll use a formula from the book. You can look it up from the cross product properties section that rewrites this cross product out here. So the formula tells us this is r hat dot r hat prime r hat minus the r hat dot r hat and then r hat prime. Okay, so this is just a formula from the book that you can look up. Okay, so see the textbook. Or you can go ahead and try to prove it yourself as well, which wouldn't be a bad idea to do. Okay, so now remember that r hat dot r hat is just the magnitude of r hat squared, and r hat's a unit vector, so that thing is just gone to just be 1. Moreover, we remember from our results before that since the length of r hat is constant, that means that r hat is perpendicular to r hat prime. So this is the result I told you to remember for Kepler's law. So that tells me that we can simplify this further. So our formula from before, a cross h, just simplifies down to the following. So it's minus gm minus r hat prime, and then just cancel out the negative signs, and we just get gm r hat prime. Okay, so now we're going to do a little bit more simplification with this. So note if I take v cross h and I look at the derivative of that, just go ahead and use the product rule here again, and recall that h is a constant vector, so the derivative of h is going to be 0. So this is just v prime cross h, which is of course a cross h, which we just calculated is gm r hat prime. Now what we'll do is we'll integrate both sides of the equation, and the fundamental theorem of calculus will tell us the left-hand side then is just v cross h. The integral of gm r hat prime is just gm r, and then since we're taking an integral we need a constant there, so we'll get some constant vector c. Now if you'll notice up to this point we haven't made any choices of any coordinate system. So if we're thinking in terms of eventually getting in an xy coordinate system, xyz, we haven't made any such choices yet. So that's what we're going to do now so we can actually start working with some equations. So our first thing we'll choose is we can choose h to lie along the z direction. So choosing our coordinates however we want, so we pick the z-axis to be in the direction of h. So that's our first step. So h will just be the scalar or the magnitude of h times k hat. Now we also know we've chosen h, and we know that r and then r cross, or we know that r and v cross h are both perpendicular to h, so if h is lying in the k direction, these things are both perpendicular to h, so they both have to lie in the xy plane. Now we saw the equation from C before, and that's just the difference between these two. So if those are both in the xy plane, then C has to be in the xy plane as well, because v cross h is in the xy plane, and GMR has to be in the xy plane, so C lies in the xy plane as well. And we're going to go ahead and use C to fix which direction we want x to be in. So so far we've only picked that h goes in the direction of k, and now what we're going to do is, if you think of grabbing a hold of the z-axis and spinning it, you can spin the xy plane, and we haven't chosen yet how we want that to lie. So once we choose which direction x will be in, now we have no more choice for y. But we can go ahead and spin the xy plane at this point without changing the direction of the z-axis, and that's what we'll do next. So here's our picture of what's going on. We have h going in the z direction, r is some vector that's moving. So think of grabbing that z-axis and twisting it, like I said, and twist it until the constant vector c lines up with the x-axis. Remember, c is a constant vector, h is a constant vector, so we can use those to choose our coordinate axes. Once we've done that, y is fixed. So now if we let theta be the angle between C and R, which is the angle now between the x-axis and R, that tells me that r theta will give the polar coordinates of the planet at any time. Okay, so certainly theta is also changing with time, just like r is. So we're now in a position to get the equation for the ellipse that our planet will follow. It's just a little bit more work. So just take the dot product of r with v cross h and substitute in what we calculated v cross h as, with the c in there. We're going to want to use the c because we can relate that to x. So you can factor out the magnitude of r so that you have r hat dot r hat here. And then we can use the definition of the dot product for r and c to get the cosine theta in there. And now note, r hat dot r hat is just 1 because it's a unit vector, so I just get GMR plus RC, where now c is the magnitude of the vector c. So now we take this equation and we solve it for r, the magnitude of r, not the vector r, and then we'll work on simplifying that. So this is just solving for r, and now go ahead and factor out the gm from the bottom. So you get r dot v cross h on the top, and on the bottom we'll get 1 plus e cosine theta, where now we've defined e to be c over gm. So this is starting to look more like an ellipse, at least the denominator is. So what we need to do now is we need to simplify the numerator so it also looks like something, so that we're getting the ellipse form that we saw before for polar coordinates. So it's a result from the book, you can look this one up again, that r dot v cross h is the same thing as r cross v dot h. And so that we can simplify because we know r cross v is h, so this is just the magnitude of h squared, which is little h squared. So now we can start to simplify this thing and get the equation of an ellipse like we saw before. So r is equal to eh squared over c in the numerator, divided out by 1 plus e cosine theta. So now just set d to be h squared over c, and plug that in, and we get e times d over 1 plus e cosine theta. And this is exactly the equation of an ellipse with a foci at the origin from what we saw before. So this proves Kepler's first law. We now have that the planet revolves around the sun in an elliptical orbit with the sun at one foci. So this all just follows from Newton's second law, Newton's law of gravitation. So we just have the final two laws to prove for Kepler's laws. So you pretty much did Kepler's second law as homework, so let's just recall that law says that the line joining the sun to a planet sweeps out equal areas in equal times. So in your homework problem, you proved already that for any general curve, the derivative of the area with respect to t as the curve sweeps out is 1/2 the magnitude of r cross v. So this is a homework problem. Either you've already proven it or you will soon, depending on when you're listening to this lecture. But for our particular curve, we know that r cross v is a constant. In general, for a general curve, it's not a constant, but for us it is. So that means that dA dt is 1/2 times some constant, the magnitude of some constant vector. So dA dt is constant, which is exactly saying the sun sweeps out, or the planet sweeps out equal areas in equal times. So that's the second law. So that one's done as soon as you do that homework problem. Now we finally proved Kepler's third law. So recall this said the square of the period of revolution of a planet is proportional to the cube of the length of the major axis of its orbit. So let's let t be the period. So this is the amount of time it takes for the planet to revolve one time all the way around the sun. And then we'll give lengths to the major and minor axes so that we can work with these. So 2a and 2b will be the length of the major and minor axes. So we'll also need the area of an ellipse. So this can be recalled from geometry, or you can prove this with calculus. The area is just pi AB. So just think of this as a generalization of the circle where the area is pi r squared. So in this case we have AB instead of r for both of them. So from above, what we had from the second law, we have that the derivative of the area with respect to time as it sweeps out is 1/2 h. So now we just use calculus. So the area swept out the whole time is pi AB. And so this is the integral from 0 to t, so that's the entire period to go all the way around, of dA dt. So this is just the total area, and then dt. And now just replace this with, we know that dA dt is 1/2 h. So replace dA dt with 1/2 h. And now that's constant, so it's easy. You just pull it outside the integral, and you just get 1/2 ht. So now go ahead and we can solve this thing for t, and we get t is 2 pi ab over h. Now we recall from before as well that E was given by C over GM, and that D is given by H squared over C. So this will allow us to calculate B and A in terms of E and D. So it's a simple calculation to just get E times D is H squared over GM, and that's exactly B squared over A if you look back at the section on ellipses and where this information is coming from. So now just take that and plug that square, go ahead and square t, the period. So I get t squared is 2ab pi squared over h squared. And now go ahead and square that out, and then replace the h squared here. And simplify, and you get that this is 4 pi squared over gm times a cubed, which is exactly what we were looking for. The square of the period is proportional to the length of the major axis cubed. And that completes the proofs of Kepler's laws.